Welcome back to the next lecture of energy conservation and waste heat recovery. So, today we will continue our discussion on energy storage systems, and what we are going to talk about today is a new technology or new class of technologies called thermal energy storage. Recall, we have so far talked about mechanical energy storage, under which we studied pumped hydro, compressed air energy storage and flywheel. Then we also talked about superconducting magnetic energy storage. So, the next class of storage device is thermal energy storage, where the excess energy is stored in the form of thermal energy. Now, what do I mean by that? Okay. So, first let us write down thermal energy storage. Okay. So, under thermal energy storage, we can further divide into two classes. Okay. The first one we will call sensible energy storage, and the second one is latent energy storage. So, I believe from your already from what you know from our knowledge of thermal sciences and heat transfer, we can figure out what this means. So, sensible energy is when you heat up a material and its temperature rises. So, you can sense that heat gain. So, that is why the word sensible comes from, and as the temperature rises, definitely the internal energy of that body, of that system, or whatever we are heating up increases. Okay. So, now if we have a device by which we can maintain that body at that elevated temperature, then it stores the heat, and later when we need that energy, thermal energy, we somehow extract it out, we remove that thermal energy. Okay. So, that is sensible heat, and as we remove the thermal energy, the temperature goes down again. Latent energy storage, however, as the name suggests, deals with latent heat, which means there is as we heat it up while storing energy or cool it down while extracting that thermal energy out of it, the substance undergoes a change in phase. And typically when we say change in phase, we normally refer to solid to liquid or liquid to solid. So, latent heat of fusion, latent heat of melting, and therefore, latent heat of solidification. So, in this case what happens is the state of the matter changes from solid to liquid, but typically as we know that any phase change method happens ideally at its melting temperature or saturation temperature, if we are talking about liquid to gas for example. Then therefore, the temperature during this change of phase remains constant. Okay. However, we store energy by changing its phase and then extract energy vice versa, right. So, that is what I am showing here, thermal energy storage. So, what is thermal energy storage? So, it allows excess thermal energy to be collected for later use. Okay. Now, what is later use? Later use can be hours, so within a day. Later use can be within few days if you are able to insulate that that energy storage device appropriately, or even months. Okay. So, for example, the summer heat from solar collectors can be stored interseasonally for use in winter. It is not easy, but it is possible. Okay. And similarly, cold obtained from winter air can be provided for summer air conditioning. Okay. Again, not easy, but it is possible, right. So, this next two bullets is the sensible heat storage and latent heat storage, which is exactly what we spoke about at the beginning. So, what we will do next is, under sensible heat storage or energy storage, what we do is we typically use a high thermal mass. So, which means the amount of energy that we store, if we know, if we recall, is Q, sorry, let me do capital Q because we are talking about energy, is M, which is mass, the specific heat times delta T. Okay. So, let us say the volume is given, this I can even write as rho V Cp delta T, where rho is the density, V is the volume. So, density times volume is mass. So, now for a given delta T, so for a given delta T, Q increases as rho goes up and as Cp goes up. So, therefore, what we need is, we need this product of rho times Cp, right. So, we need to maximize for maximum energy storage, clear. So, this is also means, this also is sometimes expressed as we need high thermal inertia or high thermal mass, both of them go together. So, sorry, I am extremely sorry, this is not rho v. So, please ignore this what I wrote here. We want to maximize rho Cp, okay. This quantity needs to be maximized, okay. So, this is the thermal mass, okay. So, this is what we need to maximize, all right. So, now so far if you remember, we have already been exposed to one form of sensible energy storage, and that is regenerative heat exchangers. So, what happens there? In regenerative heat exchanger, what happens is, when you have a hot fluid go through, then what happens is that the materials inside the regenerative heat exchanger, let us say a packed bed of sand or packed bed of pebbles, it absorbs the heat and cools down the fluid. It retains that heat, and we have to take care that it is adequately insulated, and later when a cold fluid passes through that same packed bed, it extracts the heat, or rather this packed bed releases the heat to the cold fluid and heats it up, clear. So, this is how it is done. So, this is one way of sensible thermal energy storage, okay, which we have already seen, okay. So, over here if you see, packed beds is one. Organic liquids, what happens is, here what we will do is, again in a regenerative manner, we will have a hot fluid exchange heat with an organic liquid, and the liquid will be chosen such that its thermal mass is high, and later on it is going to be released. Fluidized solid beds is another example. But however, today what we will focus on is the first one, which is pressurized water storage. Okay, we are going to talk about this in detail, and latent heat energy storage uses heat of fusion, as we talked about, and we will see some examples. So, right now I have written something, we will see more examples later, all right. So, with that introduction, let us go to thermal energy storage, the sensible energy storage, and take up the example of pressurized water. So, pressurized water storage, again I am showing a schematic, and this again is, I express my gratitude to my former teacher, Professor P.K. Nag. This is from his notes again, something that I learnt many years back, but it is still used very, it is a very good, it is a very attractive technology that is being used quite regularly, okay. So, what I have also shown at the bottom is a link which also nicely explains the functioning of pressurized water storage, okay. So, I would encourage you to go through this link and read about pressurized water storage, and this write up is more in the industrial, is written more from an industry point of view by Forbes Marshall. So, it will also give you a nice feel as to how they are using it, okay. Now, let us come here, water storage, pressurized water storage, what do I mean by that? So, the way it is done is, when we have excess energy production, or basically when the energy that is produced, let us say by a steam turbine over here, is more than what I need. So, during off peak hours, then what is done is part of this high pressure steam that enters the turbine, before it is expanded, at the high pressure stage itself, part of the steam is extracted out. Okay. So, as it is extracted out, it is fed into what is called a steam accumulator. A steam accumulator, as you can see, is actually a cylindrical vessel. It can be quite large, with and where the steam is injected through these injecting nozzles that go through it. Okay. It is actually, the steam accumulator is a big vessel that consists of water, typically at a high temperature, and in that the steam is injected, okay, through these nozzles. Okay. So, let me go back to the previous slide again. So, these are the steam accumulators where the steam is injected. Okay. So, this steam that is injected can be either at the saturated temperature or can be superheated, does not matter. So, now as the steam comes and mixes with the water, then what happens? The temperature of the water also increases, okay, and the pressure is already high. Okay. So, the pressure also goes up, and typically finally what you have is the water at that elevated pressure and at a temperature corresponding to that saturation temperature. Okay. So, that is what the accumulator actually are high pressure tanks which consists of water and steam at the saturation temperature. Clear? So, this is during off peak hours what happens. So, during peak hours what happens is the accumulators, they discharge the steam and it goes to a what we call a peaking turbine, right. So, as the steam is discharged to a lower pressure, what happens, or as this accumulator is subjected to a lower pressure, what happens, there will be a flash evaporation. Okay. So, therefore, the steam will go here and will be expanded in this peaking turbine, thereby generating additional electricity, and the pressure of the water is going to go down, right. So, this is going to happen, and during the peak hours, and the peaking turbine is going to give us the additional electricity generation that we require over and above the base load. Clear? And then during off peak hours what happens is the same steam again during off peak hours again what happens, when this energy that is required from this turbine is less than what this volume flow rate of steam or mass flow rate of steam can provide, part of the steam will again be bled into the accumulator. So, this off peak and peak, like in previous cases, keep going in a cyclic manner, okay, in a sequential manner, one after the other. So, all right. So, let us now go through these bullet points after this discussion. So, during off peak, the more steam is produced at the HRSG. What is HRSG? HRSG is heat recovery steam generator. By now, I think you are already familiar with the term. HRSG is where the steam is being produced from water using the primary heating fluid or the combustible gases, whatever you want to use, all right. Then the excess steam is bled from the turbine at high pressure. Again, remember, high pressure, at high pressure is important, because if you bleed it out at the exhaust of the turbine, then it does not help, it is already at low pressure, it will not be a pressurized storage anymore, all right. So, that is why we need it to be discharged or bled out at high pressure at the initial stages of the turbine, okay, and it is fed to steam accumulators to produce saturated pressurized water. Clear? All right. Now, during the peak hours what happens is that the accumulators discharge. So, they are exposed to discharge the water, and as a result what happens is, due to sudden decrease in pressure, there is a flash boiling or flash evaporation, and part of the steam will escape and go through this peaking turbine still at relatively high pressure, and it will produce additional electricity. And then similarly, the condensed steam goes through a condenser and is fed back into the main loop. Clear? All right. So, now what we will do next is, we are going to do a little bit of a exercise or mathematical exercise as to how we can, I mean, let us get a feel for numbers as to how much is the energy that we can store. Okay. So, for that what we will do is, let us say we are discussing steam accumulator or let us say pressurized water storage. Let us pressurized water storage. So, what we will do is we will represent the pressurized water storage in the form of a cylinder, the accumulator rather, in the form of a cylinder. Now, let us assume that the high pressure, I mean at which steam is supplied to accumulator is equal to 20 bar, and the low pressure when it is discharged is 2 bar. Okay. So, 20 bar, 2 bar. Okay. So, therefore, I can define a term called storage density. Okay. And this will be equal to 1 over the specific volume. Okay. So, 1 over the specific volume of 1 at point 1 divided by HF of the fluid, HF because it is liquid water, and minus HF2, or this is rho f or the density of the fluid at the high pressure. Clear? So, again if we just take these values and look up the steam tables, which you can do, what happens is you will see that at 20 bar the saturation pressure is actually 212 degrees centigrade, and here the saturation pressure is 120 degrees centigrade. So, if you now look at the enthalpies from the steam tables or using EES, whatever you are comfortable with, we will see that first of all the specific volume is 0011766 at the saturation temperature and pressure. Under saturated conditions, the liquid specific volume at 20 bar, and the enthalpies are 908.5 and 504.5. All right. So, let us say 1 is under stored condition or high pressure and 2 is under emptied condition or discharged. So, what this turns out to be is 343,167 kilojoules per meter cubed. Okay. Or this also turns out to be 95.3 kilowatt hour per meter cubed. Not a whole lot, because kilowatt hour, if you recall any of our most of our home appliances like a toaster or a microwave, they are rated at 1 kilowatt, around that. Okay. So, therefore, a kilowatt hour is running such an appliance. Of course, you do not run a microwave for 1 hour directly while heating at least, or a toaster for 1 hour for that matter, but any appliance like that, it is not a very high power appliance. 1 kilowatt, if you run it for 1 hour, that is 1 kilowatt hour. Okay. So, it is not a very large quantity, but it is per meter cubed. So, this gives you a feel of that if you want to really store energies in the of the range of 1000 megawatt hour daily, few thousands megawatt hour daily, then the size of the accumulator that you require, you can get a feel for that. All right. So, we will do an analysis on that as well. Okay. So, this is storage density is 1. Now, what happens is, maybe let me draw this again, the cylindrical vessel. Right. So, now what happens when we actually heat it up or when we store the pressurized water, this is at a high temperature, and then we are not going to use it right away or discharge it right away, we will discharge it later during the peak hours. So, therefore, what happens is when I store it, so let me write it at the beginning. Okay. Accumulator containing water at high temperature is exposed. Okay. Let me remove that at the beginning. I would say accumulator is exposed to a cooler ambient during storage. Clear? So, which means let us say my initial temperature or the temperature of the accumulator is T, and the outside I have a cooler ambient which is T ambient. So, therefore, what is going to happen? There will be convective losses from the surface. So, there will be convective loss, and that is going to be H A S T minus T infinity. Clear? So, what we will do is, so therefore, what I would say is heat will be lost by convection. So, therefore, when it comes to discharge and extracting the stored energy during peaking hours, I am not going to get the amount of energy that I stored, okay, and the loss is due to this. So, how do we calculate? So, for analysis, what we will do is, assume lumped capacitance method. Again, recall what is lumped capacitance method. In lumped capacitance method in heat transfer in transient analysis, we assume that the entire body which is being cooled is at an uniform temperature, right. And if you recall, that happens when Bio number is much lesser than 1.1 and so on, okay, which also indirectly means that either the heat transfer coefficient on the outer surface is very low or the thermal conductivity of the material is very high. Clear? So, you can use lumped capacitance under these conditions. Of course, the mathematical condition is there is a Bio number which should be less than 0.1, but physically what it means is that there is no spatial variation across the body that we are analyzing for transient cooling. So, which can mean primarily two things. One is the heat transfer coefficient outside is very low, okay, or the thermal conductivity of the material, effective thermal conductivity of the material is very high. Okay. Of course, the third one is the volume is very, very small, so that the spatial variation is negligible. Okay, that is the third one. But for a given volume, these are the two conditions. Now, for this case, do we satisfy that? We do not know. Yeah, probably it will be, the H will be low, I can say, but this is water, which is really in a cylindrical vessel, which is really not a very high thermal conductor, or which is not known to be a very efficient thermal conductor. But still, why do I use it? I use it because what does it mean? It would mean that there will be some variation in temperature, and at the surface at most it will be lower. So, if I use lumped capacitance and use the maximum temperature, then I am actually overestimating the losses, and therefore, it is a conservative assumption. Clear? So, I would say this is a conservative assumption. Okay. So, with that assumption we will go ahead. I am not going to go to the details of lumped capacitance analysis. I hope you all know from your heat transfer knowledge, or you can just refer to any standard textbook. What I would do is, therefore, T minus theta over theta I, which is given as the T minus T infinity over T I minus T infinity. So, what is T I? So, I would write it down over here. T is equal to T I, or initial temperature at time equal to 0. Clear? And T is definitely a function of time tau. Okay, tau is time. Clear? So, this one, it is known that lumped capacitance method will give me e to the power minus h a s time divided by rho C p v. Okay. So, many a times this one is also known as constant with the time constant. So, this term which we write as rho C v or m C p over h a is, I will denote it by T c or time constant. Okay. So, therefore, I can write it as one minus T minus T infinity over T I minus T infinity is going to be equal to 1 minus e to the power minus tau over tau c. Clear? So, therefore, after time tau, what do we have? We have this expression, the temperature at the time tau is given by this expression, all right. So, after time tau, I would also say, I would define a term called turnaround efficiency, which as we have known, as we have seen before, is energy left in storage at tau divided by original energy stored. Okay. And it can be shown that 1 minus eta t over A is going to be t minus t infinity divided by, or t I minus t infinity divided by t I minus t at that time 1 minus e to the power minus tau by tau c. Okay. And if I have to plot it graphically, it would come out to be something like this. If this is my temperature and this is my time, then I started with T I, and with time my temperature actually falls exponentially, and probably at this point, this is my, let us set tau equal to tau 1, this is, or tau 2, let us say, this is t equal to t 2. Clear? So, this is the amount of temperature that has dropped, and therefore, the amount of energy that has been lost due to convection can be calculated using lumped capacitance method, and this is the expression that we get. Okay. All right. So, that brings us to the end of this lecture, where we have looked at thermal energy storage and with details to pressurized water storage. Okay. It is one example of sensible thermal energy storage. What we will do in the next lecture is we will take up some other examples of thermal energy storage. Thank you very much.